Hi, I'm Brianna Mount. I'm graduating in the fall of 2010 at FSU with a PhD in physics. I've been working with Dr. Edmund Myers in his experimental atomic physics group, and today I'd like to talk about some of our high precision mass measurements. Most people are familiar with the periodic table, and if we just look at one of the elements in the table, fluorine, usually they give some information about fluorine. So for example here we know that fluorine has 9 protons, and they usually also give atomic weights, and for fluorine, since there's only one stable isotope of fluorine, its atomic weight is its atomic mass. So you could ask, where do people get these numbers that are in all these tables? And the answer is, for several of these elements, they get them from us at FSU. We are able to make some of the most precise mass measurements in the world. And we do this with something called a pinning trap. And we trap just a single ion in a pinning trap at a time, one single itty-bitty ion. And the basic idea behind a pinning trap is to measure the cyclotron frequency of a charged ion in a magnetic field. And the cyclotron frequency is how fast the ion is spinning around the magnetic field lines. The cyclotron frequency is given by the charge times the magnetic field divided by the mass. The magnetic field confines the ion radially, but there's nothing stopping the ion from zooming up and spiraling off into space along a magnetic field line. So we need electrodes. And in our trap, we have an upper and a lower end cap, as well as a ring electrode that traps our ion. Our pinning trap apparatus, we call it the Florida State University Precision Pinning Trap, FSU, PPT, looks like this. And as you can see at the bottom in this blue circle is our pinning trap, and it's in the bore of a superconducting magnet. And since the magnet is superconducting, it needs to be in a cryostat filled with liquid helium and liquid nitrogen. And the very top is our detection circuit. And with this detection circuit, we can detect the motion of one single ion in a trap. And to give you a better idea of what our trap actually looks like, you can see here the upper and the lower end cap, as well as the ring electrode. So who cares? Who cares if we measure the mass to the 10th decimal point or the 12th decimal point? The answer is a lot of people do. And people use our measurement in a broad range of physics, including physical chemistry, dipole moments, atomic physics, and today I really want to focus on a nuclear physics application. And this nuclear physics application has to do with beta decay. And beta decay is a decay of a neutron into a proton, an electron, and a neutrino. Neutrinos are extremely light fundamental particles that have no charge. So what is double beta decay? Double beta decay is just as it sounds. It's instead of one neutron, it's 2 neutrons decaying into 2 protons, 2 electrons, and 2 neutrinos. You can see here in this diagram, from this decay, 2 electrons are shooting out as well as 2 neutrinos. This decay has been observed in the lab. What hasn't been observed is something called neutrinoless double beta decay. This decay is very similar. The only difference is that there are no neutrinos coming off from the decay. And this has not been observed yet in the lab. The very observation of neutrinoless double beta decay would tell us that neutrinos are their own antiparticles. And furthermore, a neutrino mass, half-life measurement would give us neutrino mass information. Right now, we only know the differences in the squares of the neutrino masses. We don't know the absolute mass scale. And this is one of the most important questions in physics right now. So the people that do neutrinoless double beta decay look at graphs that look like something like this. The x-axis is the energy of the 2 electrons that are flying off from the decay. The broad peak that you see here outlined in red is what I would call the ordinary double beta decay, which has 2 electrons and 2 neutrinos flying off. But the neutrinoless double beta decay should be somewhere on the right of this graph where you see the arrows. But the people doing these experiments need to know where to look. And so where to look is at the Q value, which is the mass of the parent minus the mass of the daughter atom. And we measure those masses, give them the Q value, and then they can say, hey, you know, this is the right peak we're looking at. And if they see this peak, then they know that they've observed neutrinoless double beta decay. There are several huge collaborations. Hundreds of people are involved in these neutrinoless double beta decay experiments. Probably the most promising are the isotope pairs of germanium, selenium, tellurium and xenon and barium. Just quickly, I want to go through some of the masses that I've done at FSU. We measured the mass of 2 of the oxygen isotopes for molecular spectroscopy. Like I said, we've done several neutrinos double beta decay Q values for their experiments. We've measured the smallest known beta decay Q value, as well as most of the stable alkali masses as well. I'd just like to mention that our funding is from NIST and the NSF. If you'd like more information, please see our most recent papers. And thank you for viewing this presentation.